Okay, so moving on in the course lab, I wanted to go ahead and try this out. What we've got here is a mapping, basically, of every character to a unique number. So there's 83 unique characters in the data set. When we join all the songs and we get the unique characters, which is the set, and this outputs the amount, the length of the vocabulary. So that's the unique character set. Then we create a map, basically a character to index number. So every unique character gets a numeric representation, and we turn that into an array called index to char. This is an output of the full array char to index. So we can see the character and then we can see the index. Then we have a to-do here, and I am cheating because I'm not able to really keep up with all the Linux problems and other issues. But the idea is we're going to go ahead and now turn this into let's see what happens if we skip a line. So this is Python syntax. We need a character to index map, and every char for char in string. So this actually iterates right inside and creates an array. So right inside of the brackets we are iterating, and for every character in the string we are returning the index, and that's going to give us our numeric representation or vectorized output. And then we're going to check. Well, first we got to run this block. So the blocks are interdependent. You can't run top block without bottom block without running the top blocks, because the maps that are being set up, they're necessary. So you have to go from top to bottom and execute each one in order, because they do have dependencies on the top blocks. So the variables that are being set up, the maps that are being set up, they're all important. So this also asserts returned results should be a NumPy array. Really, this is all it's asserting. It's not asserting that you get the correct string, but let's go ahead and copy our progress, and you can see, yes, this is in line with the solution. So we can move on. So create training examples and targets. So this actually is giving you directions on how to set up the sequences, and the sequences are basically like splicing the array into chunks, and the chunks that are being spliced are the vectorized songs, and the input batch is going to be from 0 to 10, something like that. But I believe there's more to it, because there's going to be an index. Where does the I come from? Index. Oh, okay, so there's 4i in index. So we're going to be looping again over this array. So we're going to be looping. The sequence length is 10, but we're going to be using that from the variable sequence length. So we get the sequence length. So I plus sequence length, because we don't want to start at the same place. We want to go from I, from the whatever the loop counter begins, 10 sequence length size ahead of that. And for I in IDX. So this is going to go ahead and go forward. And we can close this. This is where it needs to be closed. So that's good. And then we're going to be doing the same thing, but one character ahead. So we want to let it know that if you see hell, then you need to be outputting LO. So this is the training. We're going to be outputting the output, training it with the output batch as well. So the vectorized string. So we're going to be doing I plus 1. And the sequence is going to be ahead by 1 again. I plus sequence length plus 1 for I in IDX. And that sets up this part. And they also have tests that you need to pass. So this is good. So we got a type error. Make sure your batch is functioning properly. Did we miss anything? Let's try it out in the solution set. It passes. So let's take a look. So vectorize songs, not string. My bad. This is a function. Okay, so this passed. So this wasn't too complicated, except for I'm a Python newbie, and this syntax is quite alien to me. But for you Python experts out there, you probably got it no problem. For each of these vectors, each index is processed at a single time step. So for the input at time 0, the models receive the index for the first character in the sequence and tries to predict the index of the next character. At the next time step, it does the same thing, but the RNN considers the information from the previous step, its updated state, in addition to the current input. We can make this concrete by taking a look at how this works over the first several characters in our text. So, expected output in P string F. And that's the target.
You know everything was accounted for at the Fed, right?
Step 0. What is this doing, right? So we're going through the input index in the enumeration, zip, squeeze, X batch, Y batch. This is a lot of Python going on in here. You got to know what enumerate does, zip does, and NumPy squeeze. So all of this needs to be familiar to the student who's doing these. Is there some randomness here? So this creates tuples. This, an array object of arbitrary, how to use the documentation. Okay. Fast mathematical operation over linear algebra fortran. Great. And it is random somehow. Then it gets into the model. So this was all setting up the input state, which again, like input and output, is still confusing to me. We go into setting up the model. So we're defining an LSTM. That's a long short-term memory model, which is a type of recurrent neural network. The time has come. Fill in the to-dos to define the RNN model within build model function and then call to instantiate the model.
I'm in complete control of my environment. Even though you're there.
Well, that's kind of anticlimactic. Very anticlimactic. So we're just straight passing these values.
Cheers. Cheers. So why you come to me? You're a beast, man. Plus you don't want to pull this up. We do this, I call the shots. My crew, my job, not yours. Got it? Completely understand. That's the way it has to be. That's it. That's my baby. That's what I got. How'd you get a hold of all this stuff? Get this all at that bar. Collected it over time.
Old habits die hard. Really, what I would have liked a lot more is an understanding of this. And I mean, I kind of get it. This is just the way the neural network is set up in order to predict with the time series or sequences of data. You kind of feed it piece by piece. And that's why it's so expensive to train them, because you really got to like drill it into them. Like HELLO, input is HELL, out, output what is going to be ELLO, like piece by piece. You have to teach it to recognize. What I'm really interested in is the values like here, RRN units. What is RN units? The number of units defined above to add this layer. So what is this layer? Layer 1, embedding the layer to transform indices into dense vectors of a fixed embedding size. So this is very interesting, right? And we're not really getting a lot of context here on what's going on, other than we're building a sequential model from Keras TensorFlow carries sequential model. We have an embedding layer, which I really don't know what it means. An embedding layer to transform indices into dense vectors. And we have an LSTM. Layer 2 is an LSTM with Rn number of units, call STM function. So there's a lot of syntax here, or vocab, like, yeah, there's a lot of internal vocabulary here. And then the dense is probably going to be the output, because it's the last one. So we've got 3-layer model, it looks like. And I'm not sure if I'm correct in that or not. Um, I'm not even sure where these magic numbers are coming from. Batch size, sequence length. Batch size 32, I understand this. Each batch is going to be a certain size. Build a model with default hyperparameters. You will get a chance to change these later and test out the RNN. So we get a model summary. This is what I was talking about, being able to preview what's actually going on. Total number of parameters is 5 million parameters? 5 million parameter model? With just 3 layers, we've got 5 million parameters, trainable parameters, non-trainable parameters. That's crazy. How did it end up being so large? But I guess that's the whole point of it being dense. Let's see, like it should match. Right, 5,300,000, 350,299. So, okay. Input shape 32, 100, batch size, sequence length. Prediction, shape, batch size, sequence length, vocab size. Predictions from the untrained model. Let's take a look at what an untrained model is predicting. To get the actual predictions from the model, we sample from the output distribution, which is, so now you also need statistics. Calculus and statistics and linear algebra, which is defined by a softmax over our character vocabulary. This will give us the actual character indices. This means we're using categorical distribution. Categorical distribution, what is that, ladies and gentlemen? Who wants to learn categorical distribution? Probability theory. Statistics. Like I said, you're going to need statistics and calculus, not to mention Python, and as you have seen, some pretty good, skills when it comes to managing your operating system, which if it's Linux, God help you. So let's take a look at what our untrained model is predicting. Okay. So next up is we are actually setting up a loss function, and we're going to try to train it based on our loss function. So this is important to understand. We're setting up the output and the input. here, and we have our model with its prediction. Before we train it, and then what's important to understand is this is the actual predicted text, and this is the way it's been decoded back to music. So when we come to training it, we need the Y and the pred. So we want to minimize the loss between what we expect and what's predicted. And the other situation here between you and me is define the loss function to compute and return the loss between the true labels and predictions, logits. Okay, and so the labels are Y and the logits are the prediction. And so we are just going to use a built-in loss function called sparse categorical cross entropy. And we're just passing in the Y, which is our labels. Like, let's say somebody is labeling a picture. This is a cat, this is a dog. And our logits, which is what it predicted. So again, very anticlimactic when it comes to teaching you like why this is just like a math class. And when I was going, they didn't give you a good understanding of why like what you can do with it. You know, they're just like, here, this is the one. So specifically, we will use the sparse categorical cross entropy loss as it utilizes integer targets for categorical classification. So this is just as I was talking about the image classification problem. That's why we have the word labels and logics. We will want to compute the loss using the true targets, the labels, and the predicted targets, the logits. First input the loss using our example predictions from the untrained model. Okay, so let's see what happens. Should be exactly the same. Oh, okay, yeah, you gotta execute the top. So anything that hasn't been executed needs to be executed because they are interdependent. We need to set up the X and the Y, the sample indices, and because we might be using them, let's just print everything out as well. This is the song. Ours looks different, but that's fine. Characters, it's supposed to be different because it's probabilistic. What's important is the shape. The shape matches, right? And here we're getting to some. Let's start by defining some hyperparameters for our training model. To start, we have provided some reasonable values for some of the parameters. It's up to you to use what you've learned in class to help optimize the parameter selection here. They're exactly the same, except it says experiment. Increase this to train longer. Okay. I'm not going to be experimenting. I'm just trying to get through this. Create a comment experiment to track our training run. So this is going to be interesting. Let's see what happens. Project 6S 191 Lab 1 Part 2. Dun 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 dun. Dun, dun, dun. Well, we just defined the function. We're going to call this solution. Okay, so build model to do the arguments. Where did it even get params from?
Like
Uh,
you did last time. I should have bet it got with your car. I don't want to be that instrument in my house ever again. My words, David. Father, this is all I have left of her. Where are you going? Where I belong. David. David!
they used Atom as the optimizer, instantiated an optimizer with its learning rate. Check out TensorFlow website for a list of supported optimizers. So I'm not sure how long this is supposed to be, like when it comes to a person learning to use this. And we're gonna pass it the learning rate.
Show me a way.
Okay, that's just the optimizer they told us to use. Remember, you can tweak the values here, learning rate, and it gives you a range where you can play. And let's see, the y-hat, feed the current input into the model and generate predictions. So that's just the input, which is defined as x, and then we're going to compute the loss. So that's going to be, I believe, y hat as the output. So that's the logits. So let me take a glance. Yeah, y hat, and what we expect, which is calculated here when we do our batch setup. So y and x, the input and the expected output, once again are calculated here, and then we are passing them in, and we want to minimize the loss between the expected output and the return of the model. So this will train the model to fit these two results as closely together, to actually fit into that distribution graph so that we can get it. Now we're going to complete the function call in gradient computation. Remember, we want the gradient of the loss with respect to all of the model parameters to get a list of all trainable parameters. Whoa, this is above my head. What is it doing? Complete the function call for gradient computation. Remember, we want the gradient of the loss with respect to all of the model parameters. I don't know how this function works too much. Target sources, output gradients.
The last great battle Israel would face before Goliath was against the Amalekites, a brutal nation of bloodthirsts who tormented Israel for generations.
So
King Saul was instructed by the great seer, Samuel, to keep no spoils of war, to take nothing from the Amalekites, and to slay their king, the vicious cannibal called Agag.
oh, something horrible is on TV.
Philistines are assembled.
Type error. Ah, yes. So these beautiful blocks of text, you have to remove them.
The more stone
Maybe.
changed the course of history.
Oh, isn't that great? Oh well, that's fine. Where do I have to do's? Oh, to do arguments. Right there. Sorry for the stupidity. I guess that is a valid way to make comments. Okay, let's put our API key into the solutions because I am dead in the water. I know I've executed it here. What is wrong with this? Doesn't make any sense. They're practically identical. I don't understand. What is the difference? I mean, I don't see a difference. Probably couldn't tell it not to think next time. Just give me the answer. So something is wrong, and I'm not sure what yet, with the left-hand side, even though I've literally copy-pasted pretty much everything, as you can see from the solution side, including that's wild. Did I mess something up here? Ha! Well, good luck. Right? Import comet, print comet dir. Pip install upgrade comet. Even Grok is like, seriously, brah? Project name. And looks like I hit an error even in the solutions. Well, this may be just an issue with the TensorFlow part of the assignment. So let's try to focus on the PyTorch version. PyTorch may be more stable because I've always had some issue with TensorFlow. TensorFlow has been, when they say PyTorch is easier to use, they're not kidding. And I think the main reason why is it's just much better maintained as a library. So we're going to be going top down in the solution. We're going to use our global kernel. And I think we can just hit run all. And this way we'll be able to verify that everything is working as expected. Okay, so far so good. Out runtime error. Ah, CUDA is out of memory. Well, there you go. We're at 14% utilization, but it looks like Python is grabbing 8 gigs of memory here. This is insane because I can run Oyama and I can run uh, like Mistral 3, no problem on this machine. I mean, it's not the fastest in the world, but whatever I'm doing here is just messing everything up. Um, I think the conclusion of this is it's probably better to run maybe on CPU only, and probably better in terms of like a Google Collab. Um, yeah, because there are too many barriers to entry when it comes to getting a good grasp on machine learning, and part of that is hardware setup, and another part of that is knowing the math, and another part of that, and by math I mean everything from matrix multiplication to statistics and probability, and then the actual machine learning aspects of it, where you have different types of loss functions, different types of neural networks. You saw that with just 3 layers, we were able to blow up to 5 million parameters. So it's not surprising when we see neural networks that are in the billions. Now it makes me interested, like actually how many layers are in one of those. So getting a model representation would be very interesting for something like Mistral, or even a 1 billion parameter model even. I want to know how many input layers, output layer, like, how many nodes are in the input layer, how many hidden layers, how many nodes, and how many output layers there are as well. And what's interesting is that these are the ones that we're building, they're all dense neural networks. The genius behind the DeepSeek architecture is being like they're non-dense. They have channels in them per se, and this is just me speaking as a layman, that allow for. I mean, I can't, and it's still not going down. It just took that memory and it's not giving it back up. And I had to lower my resolution and everything already. So it's intensely resource consum heavy. Just eats up all your resources. And it's not giving it up. Okay, that's it for now. Thanks for watching. I hope you had better luck. If you had better luck with this, please leave a comment.